Hello, my dear students. I'm Dr. Prasanna Gopal Shete at PVG COET Nasik. I was, and now I am in Pune. Today we are going to discuss on SE NTC Electronic Circuit subject, unit number 3, voltage regulators. As we are going to have different topics over here, the outline of the presentation, we are going to have some introduction, voltage power supply. In that, we are going to see what is unregulated power supply, what is regulated power supply, definition of voltage regulation, what are the different performance parameters of voltage regulators. We are going to study the types of voltage regulators, what are the different types of IC voltage regulators. In that, we are going to see fixed voltage regulator like 78XX and 79XX. Then we are going to see what are the different variable voltage regulators like IC 317 and IC 337 voltage regulator. We are going to discuss on the topic switch mode power supply, that is SMPS, different types of SMPS. And lastly, we are going to see what is the comparison between linear voltage regulator and switch mode power supply. My dear students, this particular unit, voltage regulators, is very, very important because we use any gadget today, we need a battery, that is DC voltage supply. And to get a DC power supply, we have to go through this particular unit thoroughly so that we understand what is regulated power supply, this of course DC, what is unregulated power supply, and all these things under that particular topic. So whichever gadget, whichever equipment we use today, as to charge that particular equipment, we need a DC regulated power supply. Hence, this particular unit is very much of importance. Let us understand that what is DC voltage source power supply. In that, we will discuss the definition of regulated power supply. As we know that we are going to have a DC voltage at the output. So to maintain the output voltage DC constant, irrespective of change in input voltage V in, load current IL, and temperature. So irrespective of the variation in all these three parameters, the output voltage DC remaining constant is called as regulated power supply. Of course, what is unregulated power supply? The output voltage not maintaining constant if there is a change in input voltage, load current IL, and temperature. So I hope you understood the definition of regulated power supply and unregulated power supply. This is the basic block diagram of a voltage regulated DC power supply. You can see on the screen there are 5 blocks. First one is transformer, where we are going to have a step down transformer in which the input is an AC voltage and output is again an AC voltage with step down in nature. So if we have input 230 volts with 50 hertz frequency, the output of a transformer will be approximately 24 volts, 12 volts, 9 volts in that form. So it is converting an AC to step down AC signal at the output. Then we have in the another block, second block over here on the screen, we have a rectifier. Dear students, we have studied different rectifiers in detail, which is going to have input as AC input voltage and the output is going to be a pulsating DC voltage. So we are going to have an pulsating DC output which is not suitable to charge a battery. So it is not going to be a DC regulated power supply which is used in radios, stereo system, computers and so on. So here if you see, we have studied in detail different types of rectifiers like half wave rectifier, then full wave rectifier, In full wave, we have studied in detail about a center type full wave rectifier and a bridge full wave rectifier. As we also have gone in detail that the bridge full wave rectifier has few advantages over center type full wave rectifier. For example, the bridge full wave rectifier has a transformer, non-center type transformer. Then we have PIV rating of that particular rectifier is VM, and the transformer utility factor is again 81% as compared to a center type full wave rectifier. So though both the full wave rectifiers have rectification for both half cycles, then also the bridge rectifier, that is bridge full wave rectifier, is the best one to use as compared to center type full wave rectifier. Then the next particular block, that is the third block in the block diagram as shown in the diagram over here on the screen, we have filter. So this filter, it reduces the fluctuation in the rectified output voltage, which is called as ripple. So in order to provide the steady DC voltage, we are using rectifier, sorry, we are using filter. Different types of filters which we have studied is like capacitance filter, inductance filter, L section filter, pi section filter, and so on. As we know that capacitance filter is used for lower current ratings, inductance filters are used for high current ratings, and so on. So here in this case, we will be studying low current ratings. So we will be only discussing about the capacitance filter as the third block over here. Then the fourth block on the screen is IC voltage regulator. That is the main topic of our today's session, where we are going to see that the input is DC unregulated for this block, and the output is DC, which is constant DC, that is called as regulated DC voltage. So this block, we are going to study different ICs over here for fixed voltage regulator and for variable voltage regulator as per our syllabus. Then if we want to go more in detail, this particular diagram of unregulated linear power supply, which consists of a transformer step down, then we have bridge rectifier with 4 diodes and filter circuit. So the output which we are going to get a DC is going to be unregulated. As we know that percentage regulation with the characteristics curve which we can see on the right hand side of the screen is given as V no load minus V full load upon V full load into 100. So the unregulated power supply has regulation poor. Hence, this is not advisable to use to charge any battery. Thus, we can see in this particular diagram on the screen that after filter, we are going to use the regulator block and then a capacitance. Then the output is connected to the load. As per the characteristics curve shown over there at the bottom of the screen, in which there is a constant voltage with respect to current. So we have VNL and VFL approximately same. Thus ideal regulation will be how much? Dear students, the ideal regulation over here comes to be 0%. That means VNL and VFL are of the same value. You have to remember that always we should have a regulated power supply of lower regulation. That means it is a best power supply. So that particular point is very important, that ideal voltage regulation should be ideally how much it should be? It should be 0%. Now let us come to the performance parameters of a voltage regulator. As we have seen the definition of voltage regulator, the output voltage maintaining constant irrespective of change in input voltage V in, load current IL, and temperature. So based on V in, load current IL, and temperature, the performance of a particular DC voltage regulator is based on the first particular performance parameter is line regulation. That means output voltage maintaining constant when input voltage varies, keeping other two parameters like IL and temperature constant. Similarly, we have second performance parameters as load regulation, which is to maintain output voltage constant when load current varies, keeping input voltage and temperature constant. Similarly, we have third performance parameters as temperature stability in order to maintain output voltage constant when the temperature varies, keeping input voltage and load current constant. So these three parameters are very important when we talk about DC power supply in our unit. The definition of line regulation and the formula of line regulations are being given over here. So we have to understand the line regulation is nothing but delta V0 upon delta V in into 100. That will give us line regulation in percentage. Similarly, line regulation can be calculated as delta V0 upon V0 upon delta V in into 100% will give us regulation, that is line regulation in percentage. Similarly, we will calculate load regulation where we have two important parameters VNL and VFL. That is VNL is no load voltage and VFL is full load voltage. And the definition of load regulation, my dear students, is given as VNL minus VFL upon VFL into 100. It is given in percentage. As we know that VNL is the no load output voltage when load current is zero, that is no load is connected. As we know that when load is not connected at all, the load current is zero at that point, and that voltage when current is zero is called as no load voltage. And when maximum current is flowing through the load, that particular voltage at a full load current is called as full load voltage. So based on this formula, we will find out the load regulation in this case. We have another formula for load regulation which can be calculated from the output resistance given over here, and we can find out V out is equal to VNL into RL upon R out plus RL, as we are finding out the VFL also over here as VNL into RFL upon R out minus RFL. So we can use different formulas for calculating the different performance parameters. By rearranging the equation, we can get the load regulation as R out upon RFL into 100%. So we can calculate the load regulation based on voltages also, which we have seen previously. And with this particular equations and rearranging the equations, we can find out load regulation with the resistance formula also, that is given as R out upon R full load into 100% in terms of percentage. Now let us come to different types of regulators. So if you see that we are going to have linear regulators and switching mode regulators. Then we have in linear voltage regulators, we have series regulator, we have shunt regulators. In series regulator, as shown in the figure on the screen, figure number A, the series element is connected in series with the load. It is called series voltage regulator. And if the series element is connected in parallel with the load, it is called as parallel voltage regulator, as shown in the figure B on the screen. We are going to study what are the different linear voltage regulators, what is switch mode voltage regulators. In linear voltage regulators, we have seen series and shunt regulator. As in the previous slide, we have seen these two types. In this linear voltage regulator, we have so many types of regulators like Zener voltage regulator, we have transistorized emitter follower regulator, we have error amplifier voltage regulator, then we have IC voltage regulator. In IC voltage regulator, we have fixed IC voltage regulator, we have variable IC voltage regulator, and lastly, we are going to see the switching voltage regulator. in which we have buck, we have boost type, we have buck boost type, and flyback type of SMPS. Now see students, then when we start with Zener regulator, it is the simplest regulator with low cost. As you go further with transistorized, with IC, with switch mode power supply, the cost of voltage regulator increases and the regulation improves as we go on towards switch mode voltage regulator. So the basic regulator also does the same thing. Switch mode power supply also does the same thing. But every particular circuit, every particular voltage regulator has its own importance. And it depends on the application where we are going to use it. So as I always tell my students that this particular Zener voltage regulator is also important, and the switch mode power supply is also important at its own place. And it all depends on the application, its worthiness to use in electronics field. Now let us see the different types of voltage regulator as what we saw, the series regulator and the shunt regulator. As already discussed, we know that series regulator means series element is connected in series with the load. It is called a series voltage regulator. And if the series element is connected in shunt with the load, it is called as shunt voltage regulator, or it is also called as parallel voltage regulator. Now, we are not going to go much in detail about the discrete voltage regulators because it is not in our syllabus. But then also this Zener voltage regulator, we know that Zener is a special diode used in the reverse bias condition, and the application of Zener diode is used as a voltage regulator. So Zener is connected as an regulator element which is in parallel with the load. Hence, this particular type of regulator is a parallel or shunt type voltage regulator. And as we know that whenever we have a Zener, we have a resistance Rs connected in series with that Zener, and accordingly the output will be regulated based on the characteristics of Zener, and accordingly we are going to regulate the input voltage DC, and we are going to get output as regulated output voltage DC. So then we have transistorized series voltage regulator, where transistor is a series element which is connected in series with the load. So this particular type of voltage regulator is which one? It is a series voltage regulator. And a Zener is used over here as to get a reference voltage which is being connected at the base, and hence we are going to have a reference voltage actually to bias the transistor. So input again a DC voltage which is unregulated, and we have output DC signal which is regulated with this transistorized series voltage regulator circuit. Now we have so much modifications in transistorized series regulator also, that as I said that we have error amplifier in transistorized series regulator and so on. As we don't have in our syllabus, so I'm not going to go more in detail about it, but we have another regulated element over here is operational amplifier. So and a transistor, of course, both are being used. So control element is transistor over here used in series with the load, and we have an error element for amplification which is used as an op amp. And so this is an operational amplifier series voltage regulator. And again we are going to have an input unregulated voltage, and we have going to generate a regulated output voltage in this particular circuit diagram as shown in the figure on the screen. Now this is a complete series voltage regulator block diagram with transistor as a control element in series with the load Q1, and we have Q2 as an error amplifier used with the Zener diode as shown in the figure on the screen, and we have a sampling at the output with resistance R1 and R2, and accordingly we are going to get the output varying from one particular voltage to another voltage, and we have a potentiometer used over there, you can see on the screen, and we will be varying the output voltage from one voltage to another voltage. So as you can see the complete the diagram, discrete diagram on the screen, with input unregulated power supply, and the output is of course a regulated DC power supply, which is based on transistor and Zener diode. Now coming to our particular interest of our unit in our syllabus, we are going to talk about IC fixed voltage regulator. As we were discussing that we have input unregulated DC voltage, that is V in, and we have output regulated DC voltage V0, and the second terminal which is nothing but connected to ground, that is called as adjustable terminal or ground terminal. So we have fixed positive voltage regulator, which is given by an IC78XX, which has three terminals as shown in the figure. On the left hand side, we have a block diagram of fixed voltage regulator, positive of course, because it is 78XX. That 8 indicates a positive voltage regulator. And on the right hand side, you can see we have the actual schematic of that IC78XX, where we have pin number 1, pin number 2, and pin number 3. And of course, we have pin number 1 as input, pin number 2 as ground, and pin number 3 as output. In different packages, we can get this 78XX regulators. This is the diagram of fixed voltage regulator with IC7812. XX means we can have different voltages at that XX value. So here we are going to have 7812. That means we have positive output voltage regulator with 1 2 indicates it is 12 volts at the output. So of course the input should be always greater than output. So input will be always greater than 12 volts in this particular case on this particular circuit as shown in the figure on the screen. So we have output regulated 12 volts with a capacitance filter C2 as shown in the figure. We have input which is unregulated input voltage with filter of course with capacitor C1, and which is connected to the input terminal 1. And the ground terminal of course is connected to the ground as shown in the figure. Sometimes we have pin number 1, pin number 2 is output, and pin number 3 is grounded. As for different packages, we have different pin configuration in that case. Now this is the complete positive voltage regulator series, we can say. Now as we know that 8 indicates it is a positive voltage regulator, and XX series means what? 05 indicates output 5 volts. 06 on the left hand side you can see 7806, it is for positive 6 volts. Then 7808, it is for positive 8 volts. Similarly we can get output for 7824, means positive 24 volts at the output. What is the minimum input voltage? Of course we know that input should be always greater than output, and approximately 2 to 2.5 volts the input should be greater than the output voltage. So if you can see over here that if the output is 5 volts, the input is 7.3 volts positive, and if the output is 24 volts positive, the input will be approximately 27.1 volts as the input, which will be always greater than 24 volts, otherwise the circuit will not work. And the drop of the output and input, which is the drop across the IC, is the dropout voltage in any of the ICs over here. So now when we talk about fixed negative voltage regulator, that is 79XX. Now see friends, that 799 indicates it is a negative voltage regulator, and XX means the output voltage what we are going to get. So as similarly what we saw for 78XX, we will have 79XX with input negative input voltage given as unregulated, and we are going to get output regulated voltage as shown in the screen with the diagram. And of course we have the terminal which is ground terminal connected to the ground as shown in the figure. So let us come to the table where we have 7905 giving output minus 5 volts. Of course, the input will be greater than 5, that is minus 7.3 volts. Because output is minus 5, the input will be greater than the output, and it will be minus 7.3 volts. Similarly, if you see at the end 7924, the output is minus 24, and the input for that particular IC will be minus 27.1 volts. I hope you are getting these things very clear that 79XX series means the negative voltage regulator series, and XX indicates the output voltage, how much we are been using for. So we have different ICs for different output voltages in each case. Now here we have a specific design of voltage regulator where you can see the complete block diagram of the voltage regulator, positive voltage regulator of course, with output 5 volts DC. Hence you can see on the screen that we have a transformer which is 230 volts primary and 0 to 9 volts secondary. As you can see on the screen, it is written, the specifications of the transformer are written over there, right down below the transformer. And then you can see that we have a bridge rectifier with 4 diodes connected. Then we have a capacitance filter C1, C2. Then we have a voltage IC regulators IC 7805. So 8 indicates it is a positive voltage regulator and 05 indicates that the output will be 5 volts DC, positive DC voltage. And then C3 is the capacitor again used at the output to nullify the ripple if it is connected at a particular distance from the source. So you can see over here that if output is 5 volts, then V minimum is taken over here as 10 volts. You can see on the screen, it is written V minimum is plus 10 volts, that is unregulated 10 volts DC. And if we have VDC, D1 and D2 drop at a time, you know that diode drop is 0.7 for each diode. And at a time, there will be 2 diodes conducting each of 0.7 volts. So it is 1.4 volts plus 10 volts. It will be 11.4 volts. And this particular 11.4 volts is nothing but the maximum voltage. So we can calculate the RMS voltage, which will be the output of the transformer. So RMS is nothing but maximum voltage divided by root 2. So it is given over there on the screen that VM is taken as 11.4 divided by 1.41. It is, we are getting it as 8.09 volts. So the transformer which we are going to use, it should be having an RMS value, that is the output of a transformer, which is calculated in always root mean square voltage, which is 8 volts. That means we can take a standard transformer which is of 0 to 9 volts secondary AC voltage as shown in the diagram over here. So this gives a complete design approach of a positive voltage regulator of 5 volts, which is used in many applications these days. Now, when we talked about fixed IC voltage regulator, we have discussed about 78XX and 79XX. Similarly, we have IC adjustable voltage regulator, as we have in our syllabus that adjustable voltage regulator are like LM317, which is again a 3-terminal voltage regulator, but it is going to have the output voltage range as shown in this particular. You can see it is from 1.2 volts to 37 volts. Dear students, what is the advantage of adjustable voltage regulator? In fixed voltage regulator, if my output is 5 volts, I cannot design that particular IC. I cannot use it for maybe 12 volts, maybe for greater than 5 volts, like 8 volts or so on. So I have to go for another IC in that case. But here what we can do, by using this IC LM317, the output can be adjusted from 1.2 volts to 37 volts. So we have a wide range of output voltage and we can use it for that particular range from 1.2 volts to 37 volts. And we can get all the voltage levels over there depending on the R1 and R2 values, which are being connected as a voltage divider network in the output of this particular circuit as shown in the diagram on the screen. Now you can see over here again we have 3 terminals. Input is connected to the positive input voltage, which is unregulated DC voltage. Then we have adjustable terminal pin number 2, which is connected through a capacitor C2 to the ground. And that adjustable terminal is connected to R1 and R2 at the center over there. You can see R1 is fixed and R2 is a variable voltage, variable resistance, that is, it is a potentiometer. And then we have C3 capacitor, and then we get the output DC regulated one, and that can be calculated by the formula given on the screen as V out is equal to 1.25 volts into bracket 1 plus R2 upon R1 bracket close, plus I adjustable current into R2. So the output can be calculated based on the values of R1 and R2. And we know that I adjustable current for this LM317 is approximately given in the data sheet of this IC. It is 100 microamperes. So if we know I adjustable current, if we know R1 and R2 values, we can calculate the output voltage. So as we were discussing, that output voltage will be based on the values of R1 and R2. So the advantage of adjustable voltage regulator is that we can vary the output range from 1.2 volts to 37 volts. Now students, you should have a question in your mind that why it is not from 0 volts to 37 volts. Why it is 1.2 volts? Because the voltage drop between the input and the output terminal, which is a voltage drop between the input and output, is always to be taken into consideration as to conduct that particular element. For example, we have a transistor connected as a control element in series with the load, as we have seen the discrete transistorized circuit. The transistor is in linear mode, as we have studied that this is all linear voltage regulators. The transistor which is in series with the load is connected in active region, and hence in order to operate that transistor in active mode, we have the drop between the input and output as 1.2 volts. Hence we have the range from 1.2 volts to 37 volts. So these all things are very important as when we discuss the transistorized circuit more in detail, as to understand how this LM317 works, because inside this particular IC again we have a discrete transistorized error amplifier series voltage regulator circuit only. Now if we see this particular diagram using R1 and R2, the same diagram is over here on the screen. We have V reference across R1. So I reference into R1 is V reference, and I reference plus I adjustable current through R2 will give us the voltage across R2. So the output can be written as V reference plus V R2. Okay, so it can be derived over here that V out is equal to VR1 plus VR2, which is equal to I reference into R1 plus I reference plus I adjustable bracket close into R2. And if we solve this particular equation, mathematical equation, we get the derivation of output voltage, which is given as V reference into 1 plus R2 upon R1 bracket close plus I adjustable current into R2. So as we have seen that the output varies from 1.2 volts to 37 volts, and V reference over here is nothing but 1.2 volts, and I adjustable current is 100 microamperes as per the data sheet. And based on R1 and R2, we have two unknown variables over here, that is R1 and R2. Two resistances are unknown. We can assume one resistance and we can calculate the another resistance to get the output as desired. So this particular example also can be solved over here. Take down the example on the screen. Determine the range over which the output voltage can be varied in LM317 voltage regulator if the value of R1 is 240 ohms and R2 is taken as 4.7 kilo ohms potentiometer. So we have a pot of R2 as 4.7 k. Assuming I adjustable current is 100 microamperes. Now see how to solve this problem. We have drawn the diagram. We know the output voltage is given by the formula which we have seen previously. We have R1 as 240 ohms. We have R2 as 47k potentiometer. So that pot will have zero value and maximum 4.7k. So we can calculate the range of output voltage in this case. Based on the formula, we know the formula which will be written over here as equation number 1. VO is equal to V reference into 1 plus R2 upon R1 bracket close plus I adjustable current into R2. Now, as I said that we have two cases. R2 is 0. We get output is equal to 1.25 volts as V reference. And the case 2, that is case B, R2 is equal to 4.7k using equation 1. So output voltage is calculated over here as 26.2 volts. That is the maximum output voltage. So using a pot of 4.7k in this particular problem, we can vary the output voltage from 1.25 volts to 26.2 volts. Are you getting this point? So this is advantage of variable IC voltage regulator LM317. So dear students, we will stop it over here in this regard, and we'll continue our session afterwards. And I will just stop the presentation over here, and we will see this remaining portion afterwards. Okay, I hope you understood. Thank you very much for patiently listening this session. Thank you.